pack. So
Question I've never seen answered about aquifers is how long does it take to recharge? I've just read a really long time.
yeah,
It's like at home that last year we exceeded our record rain total by like 15 inches of rain. I mean, we got unprecedented amounts of rain, like in the
wow,
Mid-East area, like Maryland, DC.
yeah.
And was saying, well, that's good for the aquifers, but is it? How long does it take for that stuff to actually recharge? I guess it depends on the medium.
I'd imagine it's a long-term process. So that's a good point. I mean, I guess the snowpacks of today might not really affect levels for I don't know how long, but we still need it. So, all right, today we're going to talk about particulates, although I do want to spend some time talking about lab reports just to make sure that it's super clear what my expectations are. And I did mention this on the first day, and I'm just going to remind you, I'm going to be harsh on your first lab report because I want you to take a look at my comments, tweak stuff and fix stuff and resubmit it. So don't freak out. I don't want to cause any panic attacks. Just know that that's coming. So when it comes, okay, it's not personal. It's not just you. Everyone is I'm gonna try and, even for those who do really well, try and find something to recommend fixing, even if it's not exactly on the rubric, it's not exactly spelled out, just to improve your writing. Okay, that's my goal, is to improve your technical communication with that, and that will come in handy whatever your career happens to be. You are going to have to communicate with people, so it should be helpful. So I think before we really get into things, we'll go over objectives and the overview for today, but then we'll talk about the report. I'm going to talk about objectives for today, which are really to help you better understand particulates in an occupational health perspective. We'll talk about particle properties, mostly on size, because particles aren't nice little round particles or specks. They usually have some funky shape, and so how do you measure it? How do you measure the diameter of something that's not a sphere? Things like that. We'll talk about size selection and why we care about certain sizes. Talk about the NIOSH Manual for Analytical Methods. So that's what NMAM stands for. That's I'll usually refer to it, or just the NIOSH method. But NMAM is the NIOSH Manual of Analytical Methods, sort of like the Bible of analytical methods for industrial hygiene. The EPA has their own, they don't call it Manual of Analytical Methods, but they have their own methods that they develop. OSHA has some methods that they develop as well. We're going to focus on NIOSH. I would recommend, if you focus on whatever organization best fits your use case. So if in general, if you're trying to decide between OSHA and NIOSH and it's you're not sure, let's say go with NIOSH. But if your concerns are very compliance based, then maybe OSHA is a better option, although OSHA will accept NIOSH sampling methods. Anyway, and then we'll do a lab. So we've done different things. I'm doing something I've never done for the particulates lab, and that is, well, partly because now I have equipment for it, but I'm going to be spray painting, and I'm going to be wearing this and a respirator, and we'll talk more about the lab, but I'll be doing the spray painting. You guys will be doing the sampling, and you're going to do an analysis of the results afterwards. We're going to take a look at a few things, weather permitting. If it's raining, then we can't do everything I wanted to do, but we'll do some of it. So let's talk about the lab reports.
When do you get them back to us with comments?
My goal, so if I don't meet my goal, then your turnaround time will, I will adjust your turnaround time appropriately. I mean, if I'm late, I'm not going to expect you guys to be on time with your second revisions, but so it's due Wednesday at midnight. That gives me Thursday, Friday, and Saturday. So my plan is by the end of Saturday to have it back to you. So that gives me 3 days to turn it back around to you. My deadline is Saturday night. If I don't have it to you by then I'll push your date back. But anyway, so that'll give you Sunday through Wednesday again to address my comments. And I think if we preview, then it's kind of like what you see. Oh, why am I in quizzes? Most of the so all of the rubrics except the calibration rubric follow the same basic pattern. The calibration rubric is very similar. I just tweaked a few things so that it better fits the calibration lab because it's a little different. It's not an actual assessment, but there are 5, let's see, summary, intro, methods. Yeah, 5 sections. And just pay attention to which sections are weighted more heavily. So the introduction is light. You get 1 point for a really good introduction. I don't care that much about the introduction. Now, an introduction is important, but I don't care as much about it. I think an executive summary is really important. I think that's more likely to be read by a manager or a client than, say, the introduction or some other parts. But it's worth 2 points. We'll go through each section, and you'll see the point breakdown. So executive summary, I would like a statement regarding the issue and the evaluation performed. That could be 1 or 2 sentences. I'm not super picky on exactly how long any of these are, as long as it communicates what it needs to and gets the point across. So for the calibration report, that might be something. You could talk about how calibration is important, and based on the situation, the settings, the environment within which you calibrate, it could change your could change the performance of the pump, which will affect your results at the end. So it's a general sort of background context statement. Why is this important? Why do I care? And then talk about the experiment that we did. So we had the 5 different scenarios, 1 being the proper way to calibrate, and then 4 with common errors made. Some of them are not so common, but leaving it plugged in, for example, that's common. Or using tubing that's too long, not 8 feet, but something that's not 4 inches, that's common. So talk about that. Briefly, this is an executive summary, so the whole thing is going to be like a paragraph or something. Talk about the results. And one thing I want to point out here is I would like to see some sort of number giving me some sort of idea of what the results were. So not just all words, but you could mention maybe the 2 scenarios that were the most different from the proper way. for example. I think that would make sense. Talk about something like that. Give me an idea of what some of the results were, just basic summary stuff, and a statement regarding your recommendations. I would focus on your top one, maybe two or three, depending on how long your summary is, but you don't need to cram all of your recommendations into the executive summary. If you have one that really is the one that makes sense and the rest are kind of just, well, in case if you have time, you could do these, then maybe just focus on your one and add some extra detail regarding your important recommendation. If you have 3 or 4 really good ones, then maybe you just mention each one briefly. It kind of depends. Every situation is different. I want you to think about it, use your smart brains, and come up with some recommendations summarized for your client or manager. Again, this is my personal opinion. I feel like this is, if you look at the average cross-section of all managers and clients across all industries, if they receive a technical report, I think this is more will read this than any other section. That's my thought. I have no data to support that, but I think this is really important. So word for word, if you look at the per word weight of the sections, this is the heaviest, if you looked at it that way. It doesn't have more points than some of the other sections, but it's only one paragraph and it's weighted equally with most. Introduction. The introduction should, think of it like a funnel. And I apologize to those of you who have heard me say this in different classes, but now you don't need a super long introduction. It's okay if it's, like a paragraph. But I want you to paint a picture or tell a story. Those are the best analogies I can think of. Describe for me the broad issues with whatever this happens to be. Now with calibration, it's kind of hard. You can't get into tons of detail. For this report, you're just going to talk about why calibration is important and how poor or erroneous calibration could affect your results, and thus the conclusions that you make about the workplace and health hazards. So in this one, you can't do this funnel thing. But in general, for other reports, I would like a sort of funnel structure in your introduction. So start with the broad. So this could be, geographically, worldwide, or maybe, in the nation. It could also be for all industries. You could think of it in terms of industry types. Talk about, I'll use the particulates as an example for the funnel because it doesn't really work for calibration. So let's say that, I wish this were the case, but it's not. Let's say I had arranged for us to go to a construction site around here somewhere where they're doing, they have earth movers and they're moving earth and doing a bunch of stuff. And we took samples for silica on some of the workers. So construction, here locally, if I was writing an introduction for that, I would talk about the disease burden of silicosis in the world or in the whole country and for all industries. And then I would start to narrow down. So I would start to talk about that disease in construction, or and find some statistics and say, well, there were this many cases of silicosis from construction workers in 2017, or whatever, something to start narrowing it down by the industry, by the geography, to the point where you get to your study or your assessment. And I like to think of this as a piece of a puzzle in, say, the body of knowledge puzzle. There's this body of knowledge out there, kind of just, I don't know, floating in the metaphysical world or something, but it's like a big puzzle, and there are lots of puzzle pieces missing in the puzzle. When you do your little study, you get to plug in your little piece of the puzzle into that and say, well, for construction workers at this medium-sized company in northern Arizona, this is what we found for their silica exposures. So the introduction is narrowing down to where you're going to say, we want to know what silica exposures are for construction workers north central Arizona at a smaller medium-sized company doing this type of construction. So that's the little piece of that big huge puzzle that we're going to answer and we're going to put in. And once you get to there, then you can talk about I was looking for objective because in the other bricks, I forget. So I modified this one. Although I should have modified this a little bit more. What I would like for you to have at the end of your introduction is an objective statement. Like in a master's thesis, sometimes you have a problem statement. Kind of the same idea. Okay. The other one mentions, so it has OELs. So like in silica, we should say, this is a big deal. So OSHA has published these permissible exposure limits. ACH has this threshold limit value for silica. It's like, this is what some people are doing to try and control silica. You would also talk about the health effects. So I mentioned the number of cases, but what is silicosis? You don't have to be super. Again, it's only worth 1 point. Briefly mention the health effects from silicosis. Like with calibration, we're talking about what happens if you mess up with your calibration. What are the negative outcomes? Well, your results are all messed up. You can't use those numbers. You wasted money and your time. So like with silicosis, you're going to mention the health effects briefly. Okay, it is here. The evaluation objective, that's the objective statement. And you don't have to make it fancy unless you want to, but it's got to be clear to me that it's the objective statement. So you want me to recognize, okay, that's the objective statement. But so you could say the objective of this, like for calibration, you could just say of this lab experiment wasn't a proper experiment, or exercise was to determine the effect of various conditions on flow rates of an air sampling pump, something like that. And with like if we had actually sampled construction workers, then we would say the objective of this assessment was to characterize the silica exposures of construction workers at a small to medium-sized company in northern Arizona. Make it clear. That's one thing I found in my own practice that is really important. If people know what you are trying to do, then they can decide how well you achieve that by looking at the rest of your work. But if they misunderstand your objective, then no matter how well you performed and did your assessment or your study or your project, their expectations are going to be off from whatever you achieved. Anyway, it's important. Thank you. So, end with an objective statement. Again, calibration is going to be, it's not fancy. Methods, talk about the materials used and the methods followed. And I left an announcement to clarify some of this because we didn't actually get to do it. You would have been able to see it firsthand if our pump could hold a charge. So I want you to talk about the materials used and the methods followed. Materials, think about what we use. So we had, and if anyone wants to go, we'll be back in the lab today so you can take pictures of stuff, but they're SKC PCXR8 air sampling pumps. And it is a BIOS dry cal calibrator. Like submitting a journal article, you'd have to put the manufacturer and stuff like that. You don't need to worry about that, but at least tell us like the make and the model of what you were using. For tubing, it's just Tygon tubing. For Tygon tubing, wait, we didn't use a cyclone. And this is on the announcement, not these, but the media types. It was a 3-piece PVC filter cassette. And the different media we were going to use was a 2-piece MCE, which is, I forget what the M stands for, but it's cellulose ester is the CE. I can look that up later. MCE is often used for metals. Anyway.
The first one is considered an air pump.
Yes, air sampling pump. And the second is BIOS dry cal calibrator. I mean, the official term is a frictionless piston flow meter or calibrator. But you can, feel free to take pictures of equipment and look it up later. I just need the make and model so that if I wanted to check out that stuff, I could. If I wanted to go look online and find the stuff you used, then I could. I think that's everything. We did also have a filter cassette holder. And that was also made by SKC. Filter cassette holder.
So the bias is frictionless what?
Frictionless piston calibrator or flow meter. So I sometimes people prefer a format where you list all the materials and then you talk about your procedure. I would like you to integrate the materials into a paragraph that's explaining the process. So as an example for the proper calibration, you say, explain the setup that we had, this SKC air sampling pump connected to an SKC filter cassette holder that had Tygon tubing and a 3-piece PVC filter cassette, which also had, 4 inches of Tygon tubing connecting it to the BIOS dry cal calibrator. After that, then you can just refer to stuff as the air sampling pump or the tubing or the calibrator, but kind of set things up in a paragraph, or not a paragraph, 1 or 2 sentences, describe the setup. And as new materials get introduced, like the 8 feet of Tygon tubing, then say for this scenario, we disconnected the 4-inch tubing and we stuck 8 feet of tubing on there. So I'd like it to be integrated and not like a list of materials and then talk about it. So that's the experience. And if you want to have subheadings, that's the easier it is for me to find things and read them, the more likely it is I will find and I'll notice that you did include it. And statement regarding data analysis. For this one, it's easy. You just took the percent difference of each improper scenario and compared to the proper as a reference. And that's it. None of these have complicated analyses. I just want you to mention what you did. Like, what are the numbers I'm going to be seeing in the results section? Going to be the time-weighted average? What is it going to be? For regular reports, like with silica, if we were doing silica, you would mention sending your results to the lab, an accredited laboratory. But the problem with that is if we were to actually do that, it costs money. And so we're not going to do that with any of the labs. We're going to use real-time equipment. But we will talk about chain of custody and the process of sending stuff to the lab.
So we have to take it here too.
Not in calibration. And to be honest, in maybe I'll change. Actually, for next week, we're not actually sending results to the lab, but we did in the past. And so we're going to be using their data, and you'll write it as if we were doing it once again. But there will be other stuff that we're gonna do actively. We're gonna be looking at indoor air quality, and so we will be taking measurements all with real-time instruments and infrared cameras. Some of you helped with that. All right, your results. Your results need to start with a paragraph. Describe the broad overall results. So summarize things. And in the case of calibration, you might take the average percent difference of the 4 improper scenarios. And that would be the things like we took 4, we looked at the effects of 4 improper setups for calibrating. And the average percent difference of those 4 was X.
You want the methods?
Results and discussion. So start with the broad. So it's kind of like with the introduction, you're funneling. Start with the broad overview stuff and then funnel towards the more specific stuff. And in calibration, it's going to be really short. This lab is not going to be long because you don't have that much to talk about. But mention that, then go into each of the scenarios and talk about the results of each one, the percent. And to be honest, with the format or text and paragraphs in the results section, I don't care how you do it. You could do it different ways. I guess I shouldn't say I don't care, but different approaches are okay if it just makes sense, if it's a logical flow of information. So with this one, for example, you may choose, I think this would make sense because to combine the results and discussion for each scenario in a little paragraph, a little subheading paragraph. So, scenario 2, what was scenario 2?
Well,
No media. Okay.
after the first.
Yeah. Right. Yeah. No media. So scenario 2 with no media, explain the results of what you got and then discuss why you think you saw those results. So that's what the discussion part is that's where I get to see you use your brain more, I guess, than some other parts of the report. Some of that stuff can just be kind of, okay, find stuff, put it together and put it on paper. Here, I want to see your thoughts, why you think you saw those results. And sometimes the results don't make sense. Do you have a question?
I
Okay.
was just going to ask if you want for this particular report us to say, hey, the equipment failed to work for us, so we're using previous results from other.
Either way is fine. Yeah, either way is fine. Yeah, I've got to go back and test all the pumps again and see which ones can hold the charge. Yeah, I had like let all of them charge for a day or something. This was last year, I think. Let them all charge for a day and then unplugged them, turned them on, and like let them run for 8 hours and came back and just saw which ones were still running. And there were like 2 or 3. Anyway.
You want us to describe every single experiment, words or only our specific, then reference to other failures or differences.
So describe everyone's, and but that's going to be, I mean, you'll take 1 or 2 sentences for each one to describe. So if you describe the proper scenario, then you'll just say, for the no media, everything else was as it been, except that we took the media out, for example. So it shouldn't, this will be a short report. It's okay. Just make sure it communicates, the details. Again, they're not a lot, but start with broad overall results, narrow down, have your little subsections, and then I do want a figure, and I guess I'll show you real quick a trick that I've been using to make a reference line. Let's see if it's not on the rubric, then I can't hold you to it. I'm not going to. But I would like a figure. See what I want it to look like is so you'll have your proper. Now you could number these, or as long as somewhere it's clear what the numbers, which scenario goes with which number. Obviously, there's going to be no % difference here. And then, depending on the scenario, you might have, something that looks like this. I want to give you enough guidance that you can figure things out, but I don't want to restrict your creativity, because some of you may have better ideas than I do and better ways to do things. So I'm trying to strike that balance. So for the calibration report, it could look like that, and this would be a % difference. To be honest, this is probably the most intuitive way to communicate those results. You could also consider doing something that's not % difference, where you have the proper, so in this case, the proper would be a reference line. Say, well, this is where the proper setup was, and then you have your scenarios. So you can see how they compared. That's another option. Although, again, I think for this lab, something like this is probably the most intuitive way. But if you think of a way that you feel is better, feel free to try it. If I really don't like it, then I'll let you know.
So I submitted mine. Is it open to go in and change?
Yeah.
Okay.
Yeah, if you want to resubmit, then just leave a comment and say, look at the second one. Yeah, so I'm not going to look at them until Thursday at the earliest. Probably not till Saturday, maybe Friday. But have at least one figure. Make sure it's labeled properly. So label the axes. For a figure, I want a caption that goes below the figure. If you have a table, the caption and the title go above it. Okay, so I am picky on that. I will point that out. It's one of the few things I'm super picky on in terms of formatting. I like nice, pretty figures that are properly labeled, because sometimes you could have the executive summary and the one figure, and that's all they would need. If you had a really nice figure that communicates everything in one fell swoop. That's all they need to look at, and they'll love you for that. Be like, wow, you saved so much of my time because I don't have to read your whole thing to understand what's going on.
Did you say the caption thing again?
So I believe this is APA formatting. It's the figure caption and title should go below the figure. So you have the figure and then below figure 1 and describe what's in there. For the table, it should go above. If you have a table, then it should say table 1, blah, blah, blah.
I thought it was title and then table 1 under it.
Well, when I say title,
I mean, title at the top and table 1 under it.
when I say title, I mean the name. So
Yeah.
just the name is table X, whatever. And then the caption, you'll put in some words to help people. The general rule of thumb is a figure or a table should stand on their own. If someone, thinking of old school cut and paste, or if someone screenshotted your figure, your table, and randomly like posted it online, someone should have a decent sense of what's going on. Maybe they don't know the whole context of your study or whatever, your assessment, but they can at least understand what's going on in the figure or in the table. So that's the idea. That's the general rule.
I heard that.
So again, interpret your own results. It's easy to, report what you found, but then use your brain and tell me why you think you found that. So note that this is the only section that's 3 points because it kind of is combining 2 sections in one, but it is an important section. I'd say if you have a manager or a client who is a very analytical person, that's their temperament or personality or whatever, the results is a section that they're likely to look at. They want to see the data. They're all about numbers, and so they want to see the numbers for themselves and make their own conclusions. So if you can, you could manipulate your figures and stuff to tell what you want, right? The story that you want, and still be truthful. But anyway, that's a different discussion. In the recommendations, I'd like you to prioritize them. And your most important recommendation, I want you to give me a nice paragraph on. I'm jumping ahead a little bit, and that happens when you guys write too, at least, your former colleagues. Don't forget to just kind of recap your results. 1 sentence is all. A quick summary regarding your overall results and conclusions from your results and discussion section. So you found that on average, these improper scenarios changed, the percent difference from the proper happened to be X, whatever. Then tell me, so this kind of tells me why these are important. Wow, it was that much off. The other scenarios impacted it that much. So now you really need to do this. This is what you're telling your manager or your client. And so if a manager or a client reads your report and it says everything's good, they're probably not going to read this. If you're like green light, then they're going to go. If it's yellow or red, then hopefully they come down here and they read it. But do you want to tell them, hey, you need to do this? So first paragraph is going to have a little bit of meat to it, and it's going to highlight your most important recommendation. After that, I say a bullet point list. You don't have to have that, but just make it easy for the reader, whether that's bullet points or another way, to read through the other recommendations and make sure that these are prioritized from most to least important. So that the one thing where you're like, well, this might make a difference, maybe not, or it's expensive and I don't think they're going to do it anyway, put that down at the bottom of the list. Stuff that's practical, feasible, and effective, you want those on top. Instead of showing you how to do the figure, I'm just going to show you an example, and if you want help making it, then talk to me. But this is in module 2. It's an example report. Note that this is just something I threw together. You don't want it to look maybe exactly like this, and this is kind of abbreviated and short. It's just to give you an idea. It's also on an exposure that we won't cover, so you probably don't want to copy and paste it. But it breaks it down, the executive summary, and then this is the example. So here we have, you're writing the story and telling what's the issue. Well, these aircraft assembly workers are saying, hey, our nose gets irritated, our eyes, whatever. You're like, oh, that, you apply primer to aircraft, maybe it's hexavalent chromium, red flag. So you decide to go ahead and conduct an assessment. So here I'm describing the results, but it kind of tells you also how many samples I took. Of the 4 air samples we took, 1 exceeded the OSHA PEL. So here's, a couple of numbers. You have your N, your number of samples, and the one that you want to highlight for the manager, hey, we have an issue, while the remaining 3 were below the action limit. So we talked about this. OSHA is kind of like the bare minimum. You probably want to be more conservative than the OSHA PEL. So if you have someone who is overexposed, it is something you should pay attention to and take some sort of action. And so we recommend replacing respirator cartridges. So I didn't mention this, but as we investigated, we noticed that they were using the wrong type of cartridge. And that might explain some of their irritation. And looking at you can provide 1, 2, or 3 maybe in your executive summary, but look at the nozzle. Based on the nozzle, if it's clean and working properly, you'll get less coming back at the operator. And also seeing if maybe you can pump more air into the building. Again, these are just quick. I'm not going to go through all these, but if you wanted to, you could look at it and kind of dissect each of the parts that are listed in the paragraph. These values are old. They don't apply. Don't worry about them. The overall sections still are worth the same amount that you see, but I'm not breaking it down to that sort of nitty-gritty level anymore. So you can look at that. Let's just look at the figure. This is one way I like to do it. Again, there are different ways you could do it. Where you can see I have each sample as a column and my reference lines. If you want to know how to make it so that Excel just automatically puts that in and you don't have to draw it every time, talk to me after, or we'll set up a time I can show you Excel. It's not hard, and once you know that, then you can just have it go in every time. But your goal, so the assessment has an objective, and that is to see what's going on. How much, like in this case, how much hex chrome are these people being exposed to? Your report has a different objective. What is the objective of your report? Communicate results, and especially if it's red light results, what else?
Tell them what it is.
Okay. So in the end, you want this report to spur some sort of action by management or supervisors or the workers, whoever, everyone, so that things change, so that this person is not being overexposed. Hex chrome is nasty stuff. It is a known carcinogen anyway, but regardless, whatever this was, we want it below, yes, for compliance purposes, we want to be in compliance, but also we want worker number 2, who works on the swing shift, apparently we want their health to be protected. So the report is hopefully going to spur action that results in that. So that's the objective of the report, is to make something happen. We're not going to go into diesel particulate, really. What I want to point out is that particulate is not always just the particle. For example, with DPM, you have a particle of carbon, so it's unburnt fuel. It's well, what's the term? It was, you had incomplete combustion in the engine, and so that carbon is emitted in a particulate form out the exhaust, the tailpipe. Those particles aren't just carbon, though. Often, sometimes maybe they are, but they also may have vapors and gases and other particles sort of attached to them. They may adsorb. Yeah, adsorb. I had to think of, abduction, adduction. But you may have other things adsorbed onto the particle, and so it's not just carbon that you're breathing in. There's other stuff. We don't really know, what happens when you breathe in like this kind of cocktail of stuff attached to particles. I don't want to spend tons of time on these definitions, but an aerosol is stable suspension of a solid or a liquid particle in air. And these are some examples. We won't do this exercise. I want to make sure we have time to do a spray painting. But I do want to point out some of these specifically. Dust is what you might think of. Some examples are sawdust or coal dust. One thing also to keep in mind is generally the higher the amount of energy put into creating that particle, the smaller the particle. So if you're producing nanoparticles, there's probably some intense energy in that process. Think of the national labs. So there's some intense type of energy. If you're doing basic grinding or crushing, I'm thinking of mining or construction or something, yes, you are going to get some really small particles, but a lot of the particles are going to be large. And we'll talk about why small particles are a problem compared to large. Mists are liquid aerosols generated by condensation from a gas state. Did anyone in here have some sort of physics or chemistry or something? If not, it's okay. But I just want to make sure you know the states of matter, at least that. So if you have a gas and you apply pressure and remove heat, what is the next phase or state? A liquid. If you have a liquid and you either apply pressure or you remove heat from it, what do you get? A solid. Okay, good. Sometimes, though, you get what's called sublimation. Who can tell us what that is? And an example that even high school kids are probably familiar with, dry ice. Okay. Good. So dry ice is an example. So it's in a frozen state. It's a solid, but instead of turning into a liquid, it goes into a gas. That's why it's so effective as a bomb. Is okay. That's a good point. That's true. It's a good point. I don't know the conditions that create that, but it does. That does happen too. So some mists, spray painting, in mining, acid mists are an issue. With the electroplating process, they use a lot of acids and chemicals, and sometimes you get mists coming off of that. An acid mist is not something you want to breathe. Acids have excess hydrogen atoms, and they like to give them away. Anyway, when they interact with water, it's not fun because your body is made up a lot of water, and they interact with water, and it doesn't feel good. Smoke is another type of particle. It's specifically from incomplete combustion, so kind of like the diesel particulate. Fumes. This is one thing, at least when you're talking about industrial hygiene, this is something that we get real particular on. Fumes generally refer to metals. It's a result of welding, foundry and smelting operations, hot cutting or burning operations. So officially, technically, in industrial hygiene, those are fumes. A fume only is a solid aerosol generated by the condensation of vapors or gases from combustion or other high temperature processes. So think of it as metal that has been vaporized and then condenses in the air. It doesn't have to be just metals, but generally we're talking about metals. So if someone says fumes and they're talking about exhaust, I've seen industrial hygienists who are like, no, it's not a fume. But anyway. Bioaerosols. So next week, we're going to talk about bioaerosols with mold and indoor air quality. There are bioaerosols that are super small, don't have filters that filter these. So, good luck. An air purifying respirator isn't going to stop this virus from, getting into your lungs. Lots of different types of bioaerosols, but they're biologic. So depending on who you ask, they may be living or maybe not living, but they are biologic in origin. And fibers, the key here is that they're defined generally a 3-to-1 ratio of their length to width. Length to width ratio is 3-to-1. That is a key defining characteristic of a fiber. Well, we can just look at the picture here. With fibers, the toxicity is not the composition of the fiber, but it's the shape. So the key is the shape. With asbestos, well, I think this is asbestos, but they're like little tiny spears, that go and reach the alveoli in your lungs. And, you can imagine how they may puncture and penetrate tissues, and our bodies, because of their shape, our bodies, our immune cells and respond, over time I forget the names, but there's neutrophils and macrophages and other stuff. There's cells that are designed to deal with that kind of stuff. Sorry.
Toxicity is not what? It is shape?
Yes, it's a function of with fibers. I mean, I'm thinking of asbestos specifically, but often it is the shape. It could be the composition as well, but sometimes you'll have fibers composed of materials that are non-toxic, but because of the shape and the size, then they are toxic. Anyway, neutrophils, macrophages, and those other cells are designed to go into your alveoli and into your lungs and envelop bad stuff, particles, dust, whatever, and then they pull it out. So they kind of like swallow it. You can't swallow a spear. It's the wrong shape. And so it goes in and it stays and it irritates, and your body responds to that irritation by creating scar tissue and stuff. and then you get, over time, you may end up with cancer. Inflammation is always bad. It's often a precursor to cancer. We have lots of different ways of measuring concentration of particulates. Remember this, so we're going to talk about this more, but concentration is a mass per volume. We usually use milligrams or micrograms per cubic meter. When we're talking about asbestos, there are some different asbestos or bioaerosols, for example. We talk about some different things. So does anyone know what C stands for? Colony forming units. So if it was like a bacteria or mold spores, colony forming units. This will be fibers per cubic centimeter. So that's what we typically use for asbestos, for example. This is just to give you a sense of sizes. Obviously this is zoomed in, but 150 microns is about the diameter of the average human hair. 25 microns is the largest visible particle, the smallest visible particle to the naked eye. So here we have 10, 5, I guess this is 5, this is 1, this is less than 1. And once you get into the nanoparticle ranges, then you're talking about viruses and intense processes. And well, I kind of want to talk about this now. So let's talk about it, and then we'll go back.
The MPPCF.
I don't remember what that one stands for, but the second P is per, and I know that it's an
Cubic.
imperial per cubic foot.
Yeah.
So my could be millions of particles per cubic foot, something like that. I don't know. I've never used it. If you do ever get into asbestos or mold, then you will see those other two, fibers per cubic centimeter and colony forming units per cubic meter, or whatever the volume happens to be. All right. Well, I guess I won't write on actually, let's see if I can do this. Wow. I'm getting better at that. I'm learning. Okay. So there are 3 main categories that we lump particulate sizes into.
Isn't the first word just a synonym of the last?
Where?
Inhalable and respirable.
Where?
Those synonyms?
Not in this case. Maybe depending on how you define them. But so I guess we'll go backwards. So respiration is when you have your actual respiration is when your blood comes in. Well, it should be blue because it's deoxygenated, but when your blood comes into your lungs, into the alveoli, and the O2 goes in and the CO2 comes out, that is respiration. Everything else is just it's just getting, it's buses, it's transportation system, getting it in and out. That is the actual, technically, respiration. But I am going to start with inhalable. So many of you have seen this. the semi and the smart car. Has anyone ever got on or off the freeway on one of those? You know, it's like a 25-mile-an-hour circle entrance or exit. I don't like them. I hate them, actually, because I mean, if it's not busy, it's not a big deal. But if there's a bunch of traffic and they're like 3 cars trying to get off and 3 cars trying to get on, and they've only got like 100 yards to get up to speed and move over, it just slows everything down and it's dangerous. But anyway, let's say you're on the freeway and you're getting off on one of those, or I don't know, I guess I don't know how I'd feel driving a smart car on the freeway at 70 miles an hour. But let's say you have a semi and a smart car, both gonna slow down, and let's say they slow down to 35 to try and make this turn. Which one is gonna make the turn successfully? Which one is not? The smart car could probably make that turn at 35. Usually you can, there's the recommended speed, and you can usually do it at like 5 or 10 miles an hour faster than that, safely. I'm pretty confident the smart car could make that. The truck is not going to make it at 35 miles an hour. And why? So some people talk about momentum. I'll talk about inertia. So it's the inertia of the two objects, and yeah, the inertia of the 18-wheeler is going to prevent it from making the turn. It's going to impact or go off through the guardrail or whatever. So particles are no different. They have inertia, and larger particles have more inertia. So we'll look at a poster in RASP 2 when we go over, but in your nose, there are these things. Yeah, they're concha, and I've heard the air as it passes through your nasal cavity is required to move through these twists and turns before it actually can, go past, exit the cavity and go down into your large airways. Large particles are going to impact. When I say impact, I mean they're gonna, smack into the side of your nasal cavity. You'll get snot, and if I've had days where, because I was working around diesel equipment or something, I had black snot. Well, it's because I had a bunch of carbon that impacted in my nasal cavity. Your throat has a similar function, although it just doesn't quite have as much to prevent large particles from going in, but you do have some curve here. And so some things will impact, including the back of your throat, and then you hock a loogie and you're done with it. The smaller particles, so inhalable refers to anything small enough to actually enter this tube. The whole range, but generally it's 100, 10, well, let's go on the high side as the upper limit. 10 microns all the way down to, 100 microns all the way down to 10 microns. So that's generally the size range. Now, technically, a respirable dust is also inhalable, but we care more that it's respirable. So 100 microns and lower. Thoracic means it's small enough to get past these initial defenses. It's going to come down your large airways, and it's going to make it through maybe some of these smaller airways where you can see they have lots of twists and turns, and some will impact here, 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 here. They'll impact along the way, and our body is designed to clean that up and take care of it. If you think about it, your airways, everything all the way down until you reach here is like a hall in your house. It's just a transportation network to get the good air down in to where the action happens and the bad air out. And so these are like hallways, and the alveoli again is where the action takes place. I don't know if you're in the living room watching football or the kitchen eating food or whatever. That's where your actual living happens. The hallway is just where you shuffle back and forth, right? So thoracic dust is generally, we think of it as dust in this region that does not get to the alveoli. And that is usually 10 microns down to 2.5 microns. So then we have respirable, and that's where we get particles that can actually make it into where the action happens and can start. We all breathe respirable dust every day. I would imagine every day. Our body can handle a little bit every day, no problem. It's when you are exposed to lots of respirable dust every day for long periods of time because of, say, your job, then you start to have issues. So what happens is it will accumulate. Your body will be trying to pull out stuff, but it just keeps coming back, more and more at a higher rate than your body can clear it because it can't deal with it. Kind of the same thing with like asbestos. It'll start to just scar tissue over it. Like, can't deal with this, just like seal it up. So that's kind of good, but it's kind of bad because you're losing function. And that gets blocked out, then this gets blocked out. Over time you're losing more and more function, lung function and capacity. So you don't want that. So that's our goal in trying to prevent exposures to respirable dust. So if ever someone has a concern about dust, and there's the option to look at total, in the regulations they say total dust or respirable dust, which one do you think you're more concerned about? The respirable. So pick the respirable. Unless, I don't know, if this is something where if its primary target is not your lungs, but say your nasal cavity, then maybe you are concerned about total dust. But in general, we're more concerned about respirable. So I want to describe briefly the way particle sizing works, the way we classify particles by size. There are lots of different characteristics that we look at. We could look at size, specific gravity, the shape, surface properties, and slip factor. We're not going to talk about all those, really just the size. But if a particle is small enough to be suspended in air, then that means the forces working on it to keep it buoyant are at least equalizing with the force of gravity. So gravity is exerting a force on the tiny particle, but these fluid drag forces, so gases behave like fluids. I haven't had a formal fluid dynamics class, but I had a class with a lot of fluid dynamics. And anyway, think of gases and air like a fluid. It'll behave like a fluid. It's just less dense. Anyway, so there are forces holding the particle up and suspending it in the air. If it's large enough, it'll fall out. We call that settling. It'll settle out of air. Not all particles are nice and round. In fact, I'd imagine the majority are some funky shape. What's that do with the eraser? I don't know. Okay, here we go. So imagine you have, actually I think, me just skip to here. So we have a particle. It looks like a dust bunny or something. I don't know, a cloud, broccoli head. Anyway, we can't, you know, if you were going to measure the diameter of this, where do you measure? You don't know for sure. So remember that we need to talk about settling velocity at certain velocity. So let's say we have, let's do this horizontal. We have a duct, and hide that one. We have an air duct, and it's transporting particles. So we have air moving along. It's capturing these particles from the work environment, wherever, and it's moving them along. Some particles will be so heavy that, you know, they started out in here, but, you know, there's resistance in the duct as you move along, and just kind of it settles out. Whatever the, how do I put this? The maximum velocity at which a particle will still settle out of the air would be the settling velocity. So the maximum velocity at which it will settle out of the air would be its settling velocity. So the way that we measure the diameter of a particle is we look at its settling velocity and we compare that to water droplets that are perfectly spherical. And when this has the same settling velocity as this water droplet, then we use the diameter from this droplet. It's the equivalent, let me scoot back here. It's the aerodynamic equivalent diameter. So it's the equivalent diameter of a water droplet that settles out at the same velocity as it. Does that make sense? So you have this particle, and it's a funky shape. Let's say you have 10 different sizes of water droplets. You put them all in the air at a certain velocity. You know, some of the water droplets settle out because they're big, and ours is still going, our particle, and some of the water droplets. When our particle and one of the water droplets also settle, then we use the diameter of that droplet that settled at the same time, at the same velocity, as the diameter of our funky shaped particle. Does that make sense?
So it's where it drops. That's the gauge.
Yeah, water droplets is the gauge. Now, that's not exactly how they determine it. I'm just trying to explain it in a way that maybe, hopefully, makes sense.
So the other one, the
water. Yeah, so they get a water droplet. I mean, a water droplet would be spherical. So you have, yeah, I mean, it's the equivalent diameter. So we use that number to characterize its settling velocity and its size. And we measure, so there's other things, we're not going to look at it. You know, they characterize particles by shape and by density. You can make a whole career out of particle physics, and if you wanted to, we're not going to. The key here is that its characteristics will influence its behavior in the air. So we've talked about that a little bit. A smaller particle will behave more like a gas, and it will reach the alveoli and the air exchange in your lungs. Helps determine the site of deposition. But generally, we don't worry too much about those other characteristics. We just look at the aerodynamic diameter. It's technically an equivalent diameter, but we explain that. So it's equivalent to a water droplet of that same size. we're not going to worry about this graph, but you'll often see particle distribution figures, and they're on a log scale. Just take note of that. But so you can see here, what cutoff is this? What kind of particle? 100. This is 100 micrometers or microns. Inhalable. So what's that? 10. Thoracic, and then we've got 2.5 somewhere right here. What is that? Respirable. We talked about this. You guys just got that. We won't worry about those. All right. So on to sampling. When we sample, as we talked about in the first lecture, we're trying to approximate their exposure as closely as possible. So we clip the media, we usually clip it on a collar or something. We're trying to get it close to the person's mouth. I mean, you can't, can't be like in their mouth or right in their face. We don't do that. We assume that this is close enough. We try to get it in this, what's called the personal breathing zone, or PBZ, sometimes referred to. 30 centimeters. I believe that's about 8 inches. Is that right? I don't remember what it is in inches, but try to get it as close to their face as you reasonably can. And sometimes, depending on what they're doing, the shoulder will make a difference. if they're right-handed or left-handed, and depending on what their task is, the exposure may all be on pretty much one side and not the other. It can make a big difference. So that's one reason it's important to talk to people and to watch them do their job and not just make assumptions. So I am not going to leave these on the board. I want you to remember these two equations. We're going to talk about them in a minute. But remember that concentration is a mass per volume. And volume, when we're calibrating, we talked a little bit about the bubble burette with the stopwatch. So this has soap in it. And we watch our bubble travel up the meter until it hits our 100 mils line. I guess that's what that is. No one does that anymore. But the volume is, or we're talking about volume here. We could rearrange this. If we want to calculate the flow rate for our pump, if we're doing this little calibration, we'd say our flow is equal to, it's a volume per time. Or we can think of it as that volume. It's the same equation. We've just rearranged it. Volume equals flow times time. So those are important for when we do sampling. It's also important when in our preparation for sampling. We will, if we're sampling something that we've never done before at our site, say we are at an aircraft manufacturing facility and we start to get concerned about hexavalent chromium, but no one has ever done that at our site, then we're going to have to play around with these equations a little bit to figure out some of our sampling parameters. When we sample for aerosols, we're usually using a filter. So that's what the filter cassette is. They have different compositions. I mentioned there's cellulose, PVC, there's Teflon, and there are others, but those are the three I've generally used. They do have a pore size, so some particles will pass right through them, like those viruses. It's not going to pick them up. Okay, it's mixed cellulose ester. Got that. Teflon this one is generally referred to as TFE. I don't remember what everything stands for. And then PVC. But that I had these out before class. We're going to look at these in just a minute. The method will tell you what media type you need. We'll also tell you the other sampling parameters. Yeah, we don't need to worry about that. You saw some of these. If you were to break them apart, this is a 3-ring, and it's 37 millimeters. That's the typical. There's some sampling methods that require 25 millimeters, but this is a 37 millimeter. You got your clear end, the middle ring piece, your filter and a backing pad, and then the webbing side that goes to your pump. If you're thinking of the tubing. We talked about some of this. So gravimetric, you take the weight of your filter before and after. Just know I am going to throw in a question. There is an exam question that will include this. We talked about it briefly, and it's pretty intuitive. But if you weigh your filter before your sample and after, then the mass of your contaminant is the difference between those two weights. The mass of your contaminant would be the difference between those two weights. And it's used for metals, silica fibers, and PAHs. This is a more general term, but I'm more familiar with polycyclic aromatic hydrocarbons. I feel like that should be a high school band name or something. Polycyclic aromatic hydrocarbons. Okay. All right, size selection. So if we want to just know total dust, then we don't need to worry about this stuff. We can just have our cassette with our filter, and depending on what the method says, we may have an open face or not. Now, if it's a 2-piece, we're not going to pull it apart. You take the caps off, stick it in, and you're ready to go. Or with a 3-piece, you could have an open face. But generally, in my experience, we use these with a cyclone for respirable dust, usually silica. There are 2 types of devices we use to select for specific sizes: impactors and cyclones. And they work kind of the same way as the semi truck and the smart car getting off the freeway. Impactors are often used in bioaerosol sampling, so mold. It's fairly common to use them. This is a multi-stage impactor, so we'll look at the next slide to kind of see what happens as the air travels through the impactor. But you'll have a petri dish at each level, and so you'll have deposition of different mold spores, different size mold spores at each level. So this might be the 10 micron, this is the 5, this is the 2.5, the 1, the 0.1, etc. So it's a way to break out all those particulates at different size fractions with a multi-stage like that. Generally, bioaerosols. And generally, you're not going to have somebody wearing this. I mean, it looks kind of small, but it's like this big. They're not going to have it like strapped, to their jumper or something as they try to do work. So this is the idea. Your tubing to your pump would be down here. It draws air into the impactor and has to move around. So this would be the petri dish. No, it doesn't look exactly like this. This is just cartoon, but your petri dish would be here. The particles have to make this turn to go around, and the big ones can't make that turn, so they impact here. The smaller ones make it past. They come down to the next level. You have another petri dish. Those ones aren't small enough to make that turn, and so they impact on that petri dish. With cyclones, does anyone have a cyclone vacuum or seen like a cyclone dust collector in industry? Does anyone know how they work? How do they work?
We induce centrifugal force into the airflow, heavy particulates separate and the airflow.
Okay, good. So it's using the same idea of the semi truck and the smart car. It's a different way of selecting. Usually, in this case, we're very interested in one size when we use a cyclone. So, like you saw, the multi-stage impactor, we can look at lots of different sizes. With a cyclone, we're interested in one size, usually respirable. Not always, but what happens is there's an inlet, and we can look at the cyclone we have in the lab so you can see this. You can't see a cross section though of the cyclone, but the air comes in and will spin around this center hollow tube, spins down, and as it goes down, the turns get tighter and tighter. And so more and more of the, large particles are already out. They hit the side, they slide down, and they fall out. So like if an industrial dust collector, if you see it on the outside of a machine shop or something, it looks like this was big, and it's got like a barrel underneath, or a big bucket or bin or something where the dust falls into, and then they change that, they dispose of it at whatever their schedule is. Anyway, the air moves in tighter and tighter circles until it reaches the bottom, and this doesn't really show it that well, but once it reaches the bottom, this hollow tube comes down to, not all the way down, but just above. The air is actually being pulled from this tube, and so it has to make a really tight turn, one last tight turn up and out. And so that tight turn will select, there will be a lot of particles that just can't make that turn, so they'll fall out as well. And then if we're talking about sampling and not a dust collector, for dust collector, I'm not sure what happens after this, if there's any other filter or it just goes into the ambient air. But in our filter, this is where our filter cassette would be. So it would capture only those little particles that can make all these turns and that tight turn right there. All right. So we'll turn on the lights for this. I didn't mean to print the whole manual. So I probably won't print these again. You can pull them. I never print the method except for like class. I always look at it electronically. So from here on out, we'll look at it electronically after today. Now this example is a newer version, although it's for acetone and ketones in general. We're going to look at silica. We're looking at different things, but our lab is not going to involve silica. So we'll talk about that more when we get to it. There's some important parts to take a look at. At the top, this isn't super helpful because it's for all ketones, and so they have tables down lower that have the OELs, so the OSHA PEL, NIOSH REL, and silica has the ACGIH TLV on here. So if you don't purchase the TLV booklet, that is one way you can find out what the TLV is to find the NIOSH method for it and take a look. So there's a lot of stuff there, and you can see for OSHA, this is old and outdated actually. It has the AMSHA PEL for quartz silica. OSHA now is the same as NIOSH, the NIOSH REL, but there's a little equation you have to do, and every sample has its own PEL. That's only for AMSHA now. They're the only weird ones. Anyway, you can see there some different, there's quartz, cristobalite, and tritiumite. We talked about them briefly last time. Those are called polymorphs, and ACGIH does care about which one we're talking about. The others don't. So that's helpful. If you look at this section, so this is probably, for me, the most used section. And this is where we get some of our sampling parameters. If this is, again, the first time we're doing this and we don't know how to sample for this, The sampler is the media type. So you can see with silica, it's a cyclone and a filter. So we've got a filter cassette and a cyclone that we're going to stick together. And the flow rate depends on the cyclone. So if you think of the cyclone, I don't have the picture anymore, but you know, as the turns get smaller and smaller, tighter and tighter as it moves down, and then the air moves up. If you increase the air velocity, what is that going to do to the size of particle that you select? Is it going to be larger or smaller particles? Yeah. Yes. Yes. So sometimes I get those mixed up. So if it's think of the smart car and the semi truck. If they're not going 35, they're going 65, and they try to make that turn. The smart car might not make it either, and so only the smallest. You know, I don't know what car could make that turn at 65, but anyway, you're gonna select out more small particles, and so the particles you get in your sample are gonna be smaller than you wanted, smaller than your goal was. So pay attention. We are not ever in this class going to sample for silica. It's just in case if you end up doing a job that has some industrial hygiene, like dust and noise are the two biggest things ever that are sampled. Now, if you're like in the chip manufacturing industry, silica probably isn't that big of an issue, but if it's in construction, mining, or there are plenty of other industries where silica is an issue, glass blowing, you need to pay attention to this. But anyway, so there are different types of cylinders: nylon, HD, and aluminum. We have an aluminum. That's what I'm used to, is aluminum. You got to figure out which one to use. And then for the volume, min, max, we have a range. Sorry, I thought I silenced that. We have 400 to 1,000 liters. So in a way that's helpful, but in a way it makes picking one a little bit harder. So we'll talk about how to do that. Tells us blanks, that picture's not the same, but here, 2 for every 10, right? Sampling section is really important. In the measurement side, we might be interested in this. We're not going to get into that though. You know, really expensive equipment at the lab. That's why they charge us so much money to analyze our samples. Some of this is for the lab. It's talking about the columns in the gas chromatic graph. We don't need to know that, or the injection temperature. But we might be interested in some of this information, particularly here, the estimated LOD. Is anyone familiar with the term LOD? So it's limit of detection. There are a couple of different terms that are similar. It can be confusing if you don't just conceptually separate them, especially at the beginning. But we have limit of detection and limit of quantification. Based on their names, what do you think each of them refers to? We're talking about analysis of chemicals or substances in a lab using stuff like gas chromatography, X-ray, fluorescence, stuff like that. You know, expensive machines. Close. So it's not necessarily size, but the mass, the amount. So with limit of detection, it's the smallest mass that they can detect. Now, let me just write it. I'm mixing capitalized and lowercase. So it's the smallest mass that they can detect with the equipment, but that doesn't necessarily mean that they can quantify how much. So I can say, it was present. It was detected, but we don't know how much. So if you're looking at these and you're looking at a scale of masses, let's say, this is 10 micrograms. This is not the scale, but 1 microgram. The limit of detection might be, let's say it's right here at 1 microgram. So if there's at least 1 microgram, they can detect it. But let's say their limit of quantification is, again, not the scale, but let's say this is 5. Let's say the limit of quantification is here. If there's this much, then they can tell you how much is there. They can say, oh, it's 5.2 micrograms, or 12, or whatever the number happens to be. But below this number, they can't measure it, but they can tell you it's there. And then below this number, they can't tell you anything. That is as we talked about last time, that would be a non-detect. Below that level is going to be a non-detect. Questions on that? So when we sample, we hope that our concentrations are low, but we do like to have a number. We don't want to have to say it was a non-detect. We'd like to, there's some things that we can change to try and get detection and even get quantification, even if we know the levels are low. So we still have a number that we can plug into our data set later. We'll talk more about what you do with when you have more and more data, you collect things that you need to keep in mind. So we want enough to have detection. We want enough for quantification, although we don't know that here. So going back to our equations over there, I'm going to use this side so we can keep those up. We have a range of volumes that we need to hit. So that means, so we can adjust our flow rate. Well, this is not the same one we're looking at, but we can adjust our flow rate and the sampling time to modify our volume. Okay, so if we sample for longer, what's that going to do to our volume? It's going to increase it. If we increase our flow rate, what's that going to do to our volume? It's going to increase it. So we can, and luckily they're directly related. So increasing or decreasing one of these is going to increase or decrease our volume. So we can play with these a little bit within certain ranges. Sometimes the method says this flow rate only. So actually, like with silica, if we have an aluminum cyclone, this flow rate only. So we can only play with the time. We can't play with flow rate. We're dealing with silica, so we're going to stick with that. And let's assume we have aluminum cyclone. We need to make sure we hit that volume. I should have it up here, but 400 to 1,000 liters. We want to hit this volume. We also want detection, at least detection. And what is the limit of detection for silica? The estimated LOD? 5 micrograms. So here's our volume. We have a range. We have a mass. It's a target mass. We want at least this at a minimum. And that was 5 micrograms, or 0.005 milligrams. Okay. We want to make sure we hit this. How can we? So think of these two as the same thing. They're the same thing. Is there a way we can combine these two expressions so that we can try to hit a target mass in our sampling? Okay, so we're going to talk about concentration. Assume that we have a guess on concentration. Okay, so what we can do is, because V equals this, just plug this in here, and then we can manipulate. So we're going to take that and plug it in. You know, once you're comfortable with it, you can just do whatever. I mean, we're going to plug that in there. So we have concentration equals mass divided by flow times time. So a couple of things. This is the V. So these are the same thing. So we're just plugging that in. We have a guess for concentration, but really the thing that we can play with the most here is our time, our sampling time. We are given a flow rate. We can't change that. 2.5 liters per minute. So we know our flow. For concentration, let's, well, we won't go to it. You guys are going to become pretty familiar with the NIOSH health hazard evaluations, but can anyone remember the average silica concentration from the health hazard evaluation from the quiz? I think it was one of the questions.
You asked for geometric mean.
Oh, the geometric mean. That's even better.
Thank you for.
0.4.
We need to talk about geometric mean. We'll talk about it. Huh?
You're in curve
It's
question?
0.4 and 1.4. I remember 0.4.
I don't remember what it was, but let's say it's 1.4, 0.14 milligrams, which is pretty high. So I'm pretty sure it wasn't above the old Pell. It's above the new Pell though. Well, let's say 0.14 micrograms per cubic meter, which would be the same thing as 140 milligrams per cubic meter. So let's put that over here. 140 milligrams per cubic meter. The idea there is we've never sampled for this before at our site, but say we have a sister site that's pretty similar to ours, and this is their average, or if we don't know anybody, we could look up a NIOSH health hazard evaluation, see what the average was for their process, and we're just putting it in as an estimate. And even if there's nothing like that available, we could say, well, I hope that it's 10% of the TLV. And then for the concentration, I'm going to plug in 0.1 times the TLV. We're kind of guessing. I just said, I want it to be 10% or less. So I'm just guessing. At this point, we're just some of it is kind of guess with the concentration. So let's say we're borrowing this number from a sister site who has done sampling, and so they have some data. So we need to manipulate this so that we're solving for T. Well, let's do it step by step. We're gonna multiply. We're cross multiplying. So I'm multiplying by T and dividing by C, multiplying by T, dividing by C. So those cancel, and I get T equals M over Q times C. We need to make sure the units work out though. So I'm going to use my line that I like to draw. Where am I going to do this? I'll do it low. So I want a time, and I want it in minutes. That's what I want at the end. So one thing I'm going to do is I'm going to start with something that I know has minutes in it. Flow is a liters per minute. So I'm going to start with that. And I'm going to make sure that minutes is on the top because that's what I want. And we have to use 2.5 liters per minute. So 2.5 liters per minute. Now we got to cancel out these liters. Do we have anything else that has a volume in it? So we have mass, concentration. Concentration has a volume. So we need to make sure that our concentration cancels out here. Our concentration is 140 micrograms per cubic meter. Now that's a little bit of a problem, not too bad though, because our flow is in liters, our concentration is in cubic meters. We need to convert and cancel them both out at the same time. Luckily, I remember this is one that would be good to just memorize. It's an easy one. That 1 cubic meter equals 1,000 liters. You just remember that. That one's easy because it's 1,000. I remember that, so I can just plug this in. I put 1,000 liters on top so that these cancel. And I put 1 cubic meter down here. This is the same thing as saying 1 over 1 because these are the same thing. So it doesn't matter. We can add these in all day if we want, if it helps us. So my cubic meters cancel out. That's good. But now I have a mass here that I've got to deal with. And luckily, that's all we have left is a mass in our little equation. So I know my limit of detection is 5 micrograms. Luckily, we went ahead and converted in our head, so we don't have to do it on the line, but those cancel out. So now all my units are canceled out, and all that I'm left with is minutes. So if I do that math, it should tell me the minimum sampling time I need to get detection. So it should be really low. Hopefully it's really low, especially with a concentration like this. Here's a well, so someone go ahead and do the math for that. And
1.4 minutes.
Sorry?
1.42 minutes.
So not very much time at all. Which, in a way, you kind of hope that struggle a little bit to get collection or detection, because that means that you have a high concentration in your workplace, and it's easy to get detection, but then it means it's hard to control it on the back end. Is that what everyone else gets who's done it? Should be 5,000 divided by 3,500. So that looks about right.
2.5 times 140.
Yeah,
2.5 or 25?
It's 2.5.
2.5.
Yeah.
Oh, okay.
So it's 14.
14.
Yeah, 14.2.
I was reading 25.
Oh, okay. I know it's kind of low on the board, so I apologize. All right. So we know we'll say 15 minutes. We've got a sample for 15 minutes, which is very long. Let's say, so, and this concentration, 140 micrograms, is well over the PEL. The PEL is 50 micrograms. We're at 140. We're almost 3 times the PEL. So that's a really high, you know, a few years ago that wasn't that high, but places had way more than that all the time. But let's say that it's not quite so high. Let's look at 10% of the TLV. So when we walk out into this workplace, we don't see a bunch of dust. We're not, kind of swimming through to go wherever we're going, but it's actually pretty clean looking. We know we generate some dust. We think this is where it's at. If you change that, what does that bring this to? So this number went down. So what's going to happen to this number? It's going to go up. 400 minutes, okay. So with that, it's 400 minutes, which if we're trying to get an 8-hour day, how does this compare to an 8-hour day? It's close, right? So just 80 more minutes and you've got the full shift. It rarely is the full day though, because the crew will have their morning meeting or whatever, stuff happens, and then maybe they have to get off the site early or something. So anyway, it's usually less than 480, but 400 is a pretty good amount. So that is how you determine your sampling time, to make sure you at least get detection. But there's one more thing we need to check, and that's the volume. So if we sample for 14 minutes, are we going to have enough volume? I should erase something or use a different color here. 14 minutes, so let's say 15 minutes. If we decide, okay, we're going to do the bare minimum, we have 2.5 liters per minute, and we have 15 minutes. How many liters are we going to have?
35-ish, or way below them.
Yeah, maybe 40, maybe? I don't know. But, right. We're supposed to have 400 to 1,000 liters. So we're not in the range. So even if, we shouldn't have a problem getting detection. So it is possible to overload, actually. And that's something you have to pay attention to. Some of these other details we're not going to look at, but sometimes it will mention overload. You don't want that either. We'll talk about what happens with gas sampling. It's not overload, it's something different. But so if you look at this third page up here, it doesn't talk about overload, but that's typically where you'll find something like that. It'll say avoid sampling 10 milligrams or something like that. If you get 10 milligrams, you have a big problem. Anyway, so you can usually find that. If it's an issue, you'll find it in the method manual. But obviously we need to increase our sampling time here. Let's do one more little bit of math. So let's say this is the first scenario with the first concentration we used. We have to have a minimum of 15 minutes, but it doesn't get us enough volume. What is the minimum sampling time then to meet our volume requirements? So we know the concentration is good. Like we're going to have plenty to detect, but we need more to meet our volume requirements. So we can rearrange that first equation where V equals Q times T. So it's V over Q. So we divided by Q, divided by Q, and we get this. So if we're going to plug in 400, so our minimum volume into the V, and we can't do anything about our flow rate. I'm not going to do the whole line like usual. When I don't know how the units work out, then I do that, but I know it's going to work out. Those are going to cancel. We're going to get minutes on the top. So to meet our volume requirements, how long do we have to sample?
What are you crossing out on the V equals Q times T?
The Q. So I don't remember all the versions of an equation. It's just the way I think. I remember the initial standard equation. So V equals Q times T. And then I modify it as I need to. So that's what I'm doing here is I know that this is true, but I want time. So I divide by Q on each side to get just T by itself. 2.5, sorry. Huh? 160 minutes? Okay. So you have to keep that in mind as well when you're looking at your minimum sampling time. Keep the volume in mind, keep detection in mind. So we're about done. We just went over that. Okay, one last thing, and then we'll take a little break and head over.
160.
Yeah, 160. So for this lab, I would like you to use the Evade software. Let me explain what we're doing and why it's Evade is even, we're looking at it. NIOSH has developed software that lets you overlay video, or at least maybe not overlay, but compare side by side video and the real-time concentration. So you can look at tasks, specific tasks that may be increasing exposures. So when someone does this, then there's a spike. So later you can go back and say, look, you show the video and the spike and say, when you do X, you get a big spike of whatever. So stop doing that, figure out a different work practice. Anyway, so the software lets you put the two together and then you can view it. I just want to show kind of what it looks like so you can see where this is at a mine. I didn't take the video. It's a head cam video. You can, so the department got me a body cam that's for police, but I got it for the purposes of this class and research. Although I think it'll be short enough today that you can just shoot it on your phone. So have someone in your group shooting video, and then we'll be measuring particle concentrations with this. It's called the side pack. It's got I also want to show you real quick. If you just search for NIOSH Evade in YouTube, the first video that is one that is from NIOSH. It is I'm curious to see. Okay, it's not a viral video, but it's a tutorial on how to use the software. Okay, so if you can't figure it out at first, then use the tutorial. That used to not be there, and I figured out how to use it. I think you probably could as well, but it's not super intuitive. It's government produced software, but it's not that bad. Anyway, you can go there. You can see how to do stuff.
Are we having to download this or what?
Someone in your group will need it on a computer. Yeah, it's not a big piece of software. It's it might be like 1 meg. It's pretty light.
Is it on like big computers or anything like that?
It's not. You could, if you're gonna do this in one day, you could sit down and install it and do it on one of these computers. At midnight, it'll flash and it'll be gone. But so you can, it's, at least I think you can. They just changed our permissions on our computers, the faculty and staff computers, so that we can't install whatever we want now. so I can't install it on mine, actually, on my work computers. Although I already had it, thankfully. But so I don't know if that has changed for these out here. Has anyone installed anything on these recently? If no one in your group can get it on their computer and get it up and running, let me know, and we'll figure something out. Sorry?
Are there cameras in the lab?
Well, no, but I think it's easy. It's not gonna be a long lab, and so it'll be 2 or 3 minutes, 2 or 3 times. So 2 to 3 minute videos. It's just it's not a real. I mean, it's a fabricated scenario for the purposes of the class. The goal is, well, it will be just I'll tell you when I'm starting the data logging on here, and that's when you'd want to start recording. But you can go back and change the alignment of the video to the data if you need to. Like if you started recording before I start this, you can slide it around. All I'm doing is I'm gonna have I gotta make sure Adolfo is around. He has a trash can for me. I'm going to set up a big trash can in the lab and spray paint a swing that I made for my kids. And I'm actually just putting a coating on it. But anyway, I'll have that on. I've got my respirator and stuff over there. So that'll be inside. We're going to do it inside for a few minutes. You guys can stand back, and afterwards we'll open the doors. We're going to do it on the little porch just outside on the back of Rask. And then if it's not raining, then we'll do it out in a completely open area. And so one of the objectives for this lab is to compare those 3 situations: inside in a kind of porch patio where you have 2 sides blocked and then 2 sides that are open, and then out in the open where you have none. And just see what sort of effect that has on my exposure as I'm painting. And you'll have the video to overlay, so you'll see what is going on when there are spikes. What am I doing? I think that's it. Are there any questions? I did want to talk about this instrument real quick before we head over. Guess we could do it while we're there. But we are going to use a cyclone. These are newer. They're nice. So you can do personal sampling or you could do area. The personal sampling this is what the tube in the cyclone is for. If you're doing area sampling, they have these are impactors. So here we have a cyclone. It's little. But we've got a cyclone for respirable particulates. And we have impactors. They have different cutoff sizes. So this says 1, 10, 5, 2.5. What do you think it's referring to? Microns. Right. So we just have the regular inlet. So there's no impactor. It's the standard inlet. Our size selection is going to be happening in the cyclone. One thing we're going to do over there, I'll talk about it now and then we'll do it, but a lot of real-time instrumentation requires you to zero it before you do any sampling. I can't remember I don't think we talked about this yet in this class, but what do you think zeroing means? Or if you know the answer, then you can say it.
It's like zeroing a scale.
Okay.
Whatever the current pool is created, that's the standard is where you start something and generate. We can talk about.
Good. So if you wanted to show that you weigh less than you actually do, you'd put like a book on the scale,
You put 100 pounds on there,
zero it,
step on
then step on it. Wow, doing awesome. So that's the idea with this is it's reading particulates. You don't want to go to a really dusty area and zero it because then you're going to get negative numbers and you're going to think, what the heck? So when we zero it, we don't want to be somewhere. Actually, just walking on the carpet will stir up some particulate, but generally indoor spaces are pretty particulate free. I mean, I think we breathe a lot less dust than if we lived outdoors. So, so we are going to zero it. So that's something to remember for your report in their methods. And it's important to remember just as you do as well. So we don't calibrate like we did the pumps, but we would zero this before we use it. All right, we'll start over there at 15 after.